Hi, I'm Tom Siewert, and today we're going to look at the most important element. People like to make lists of fastest, biggest, all these kind of things, and we're going to try and come up with the most important element. What is that? Well, here's a list of some possible choices. Certainly, we know we need oxygen. After all, how long could we live without it? Another one is nitrogen. It's a key component in amino acids. Next one down, carbon. It's one of the building blocks of life. Another key important choice, hydrogen. Well, we need hydrogen to join with oxygen for water. We need calcium. Every morning, most of us take calcium pills to make sure we keep our bones strong. Iron, we know we need that in our blood for hemoglobin. Phosphorus, that makes strong bones and teeth. Plus, there are another 19 essential elements needed. If you look at your vitamin pills, you'll see many of these listed there. And of course, when you go to the grocery store, they're all out there on the shelves. It's a huge number of items that are needed for life. So which of those is the most important? Well, they're all essential, so it's hard to choose which one is most important. It's true that you might live longer without some than others, but sooner or later you're going to be in trouble unless you have all of them. So let's ask a slightly different question. Which of these elements had the widest range of essential functions? I would nominate carbon. There are more carbon-containing compounds than all those without carbon. Also, carbon is one of the building blocks of life. Organic compounds number in the millions. We don't have time to cover it, but if you go online, there's just millions of organic compounds. Also, it is one of the few elements that can form long chains and three-dimensional structures, actually up to 4 bonds total. It not only joins with other elements, but also with itself in some very interesting ways. Diamonds, graphite, coal. Incidentally, coal is similar to graphite, but messier and has a more three-dimensional structure. And then there's fullerenes. The question might be, what are these things in more detail? Well, organic compounds are defined as any compound that contains carbon, and it usually has hydrogen and sometimes nitrogen as well. Organic comes from the same root word as organism, which is usually defined as relating to life. Typical examples of organic compounds include sugar, starch, and amino acids. A typical example of an inorganic compound would be limestone, which is really calcium carbonate. It serves as a reservoir if we need more carbon for life. Another feature is that organic compounds are fairly stable. We have food in our pantry that lasts for years, and the same thing is on store shelves and on farms. We can keep these things for the future. We also see organic compounds as dead trees in a forest. Also, for hundreds of years, organic compounds have held up medieval buildings as the lumber in them. The La Brea tar pits are another example of organic material that's been there for thousands of years. And of course, coal beds have been around for thousands of years as well. What I thought was very fascinating, at Masada in Israel, they found a date palm seed that was still fertile. They were able to sprout it and grow it, and now they have 1900-year-old history of date palms that have been restored because they were no longer in existence in the country. And of course, we see these in our houses with furniture and paper as well. A key part that makes organic compounds is their bond strength. Covalent bonds, which are what are in organic compounds, are fairly strong, which explains that stability of compounds for years. Coincidentally, that bond strength is similar to the energy of that in typical incident photons, light. In other words, the light coming in down to the surface of the planet has similar energy. And that's very important because, the next bullet, we see that light harvesting complex. That's a technical term for what works to reduce the carbon dioxide and store it in new compounds. This is really how photosynthesis works. Thus, the light harvesting complex in plants can efficiently break the bonds in carbon dioxide and store the energy from the light in new compounds. Then, in turn, these compounds are broken down later and used by other biological processes like digestion. So this is how we get the energy coming from plants. There are weaker bonds around, like adhesives or rubber bands, but we know in both those cases, those things will break down. A rubber band will effectively degrade over a period of time. Adhesives lose their stickiness, where carbon bonds are much stronger and last for a long period of time. How does this work? What is the real process? Well, light energy is converted to chemical energy. Again, the equation is carbon dioxide plus water plus energy, that's what's coming from the sunlight, gives oxygen plus glucose. One interesting factor, it's very high quantum efficiency. In other words, it effectively uses the energy of the light into the plants. Animals do the opposite. They take the glucose, react it with oxygen in our bodies, for example, to give us energy plus water. Let's talk a little bit about this light harvesting complex. It's something built out of organic compounds. So it's like almost building a photosynthesis factory out of organic materials that works to reduce carbon dioxide to make more organic materials. The light harvesting complex has pigments. They're called antenna proteins that capture the energy of the photons. Then this energy is transferred over to another spot where it reacts and forms the glucose. The antenna proteins come in different wavelengths, so they're sensitive to different kinds of light. This means that the process can still function in muddy or deep water, where certain wavelengths are filtered out. So here we have a process. We have a factory that's taking light energy and putting it into glucose that we can use. Now that glucose is known by another name because glucose is one of the carbohydrates. The name carbohydrate literally means carbon and water together. It's a generic term that includes various compounds with a formula of carbon, hydrogen, and oxygen. They're found in various shapes. They're called isomers and combinations because you can have a double molecule as well. So three common types that we know well are glucose or dextrose, sucrose, which we use all the time as table sugar, and fructose, another one that's found in fruit. Other types of carbohydrates are lactose, which is milk sugar, galactose, and maltose. All of these are energy sources for biological systems and only differ in their structure. They're all broken down in bodies to get the energy out of them. Carbon dioxide is very unique. It's among the few oxides that are gaseous, which means it is ideally suited for photosynthesis on land. Thus, carbon dioxide can easily reach plants and to the sites within the light harvesting complex in the plants where it is converted to sugar. Also, carbon dioxide is soluble in water. That means it can reach waterborne plants as well. And also that solubility is important for waste removal through the blood system of animals. So carbon dioxide goes out through our blood. The carbon comes in as a form of the glucose or carbohydrates. So there's a process transferring it back and forth. Let's look more and see what's happening in animals. The bonds in glucose are weak enough that they can be broken in biological systems, and the chemical energy is used by the cells. That's what really works in our body is chemical energy. We need to oxidize that material, and so we need oxygen coming in. So our systems and animals, we take oxygen through the bloodstream in red blood cells and transport it to the cells where it's needed. After the reaction occurs, the waste products, water, carbon dioxide, and heat, are transported by the blood away from the cells. Some carbon remains and becomes bones or shells. We think of that often as coral in the ocean. If we look at the whole cycle, try and look at the big picture, there's a net transport. Plants take the energy from the sun and store it in a form appropriate for animals. There's carbohydrates, but also plants make proteins and fat. Look at the side of your peanut butter jar and you'll see a listing of the ingredients in there. It has the carbohydrates, protein, and fat all listed coming from the peanuts. Animals use that energy to live and recycle the waste products back to the plants. And there's many other small subsystems and trace elements involved in a complete cycle. We don't have time to cover all those details, but the basic system cycles energy and products between plants and animals. Chemistry defines oxidation as the gain of oxygen and reduction as the loss of oxygen. Oxidized compounds have less stored energy and reduced ones have more. Carbon dioxide is an oxidized one. Plants reduce carbon dioxide from its oxidized state as a gas and store the energy as glucose. On the other side, animals oxidize the stored energy and return it to the air as CO2. Again, it has to go through the bloodstream, back out the lungs, back into the air. We can also burn reduced carbon compounds like wood, oil, gas in fireplaces, furnaces, and engines, releasing the energy for our use. Oxidation and reduction. We find things around us that are oxidized. Rust is iron oxide. It has to be reduced in a chemical process to make it into iron that we can use. In your kitchen, you can partially burn sugar to make caramel. So another good use, there's some home research you can study how to oxidize sugar to make caramel, a great product. There are residual sources of carbon as well. In addition to powering life, some of the carbon dioxide that's ingested by living systems remains afterward. It remains as bones, for example, calcium carbonate. We'd see it in forests as fallen timber. In coral reefs, we have the calcium carbonate shells of the coral that have built up. Coal is another one of those reduced carbon compounds. And oil. Coal effectively is highly baked plant material, similar to charcoal. Where does this carbon exist? It's really in the world around us. It's a common element in the Earth's crust at 0.03%, which is a huge number of carbon atoms out there. Most of it's combined as oxides, and we see 1.8 times 10 to the 18 tons of it. We all know we have some carbon dioxide in the atmosphere. It's 3 times 10 to the 12 tons. That is 3 million tons of carbon dioxide. Some is as coal. Now we have 1.3 times 10 to the 12th. So that is 1.3 trillion or 1.3 million tons of coal. Oil is 1.6 times 10 to the 12 barrels. There's a lot of natural gas, 10.9 times 10 to the 15 cubic feet of that. And some is forests. And of course there's other sources. There's miscellaneous products like the biomass in the ocean. Now, unfortunately, we see mixed units. We think of some things like coal in tons, oil in barrels, natural gas as cubic feet. Let's try to combine those in standard similar units. So here's our annual usage in tons. Coal, we use 7 times 10 to the 8th tons of coal every year. We use 4.5 times 10 to the 9th tons of oil. We use 4 times 10 to the 9th tons of natural gas. And then finally, forests continue to grow. We harvest 1 times 10 to the 9th tons for both wood and paper. Notice that we use 10 times more energy than what forests produce renewably. That means we're going into reserves. There are coal reserves, there's oil reserves, there's natural gas reserves. We need that to supplement what can be done renewably by forests. What are some of the implications of this? Those reserves have fueled the Industrial Revolution, literally fueled it, because we use those carbon sources for energy. But again, 90% of the reduced carbon deposits are not renewable, the ones other than the forests. So our demand for carbon-based energy cannot be met by plants alone. And of course, there's a great focus now on renewable sources, water power, wind power, sun power, and they're slowly increasing, but it often takes carbon-based fuels to manufacture these structures. For example, we use carbon-based fuels to make concrete that would build a hydroelectric dam and also make the materials that are for the generators. We use carbon-based fuels to make solar cells, and we use them to make wind power towers. The bottom line, it's difficult to break our addition to reduce carbon. What are we going to do? Well, let's look a little at history. Advances in civilization are often defined as ages. That's when we learned how to make and use these materials. One is Bronze Age. That's when we learned to produce and work bronze, which is an alloy of copper and tin, into tools. Iron Age is when we learned to produce and use iron. Unfortunately, these metals are all found as oxides. They're in an oxidized state in ore. So you find a mountain that has iron ore, a mountain that has aluminum ore, a mountain that has copper ore. We need to reduce it in a refining operation and then work it into the shape we want. The reducing and refining operations are endothermic. That means they need energy, fuels to operate. Which brings us to something called thermodynamics. That's the science that describes the relationships between heat and other forms of energy. It describes why some reactions run spontaneously, exothermic reactions, while others require external energy, endothermic reactions. So let's go back to photosynthesis. Photosynthesis is an endothermic reaction that converts sun energy into glucose. So it takes the sun energy, stores it in glucose, so it requires the sun energy to operate. In return, our bodies exothermically oxidize the glucose back to carbon dioxide and water. So there's that back and forth system, both in photosynthesis and oxidation in our bodies, and also in metal ages and the oxidation that occurs later when iron rusts and other things break down. Overall, things want to run down, things want to oxidize. On the next page, we're going to show something called the Ellingham diagram. This is something that shows how the stability of oxides change with temperature, and also how do we remove oxides from metals so that we can work with the metals. On the very top of the diagram, you'll see where reduced metals, that's the metal and not as an ore, is stable. If you look at it, most lines slope up to the right. There's one line that slopes downward. That is carbon reacting with oxygen. What this means is that as the temperature goes up, the carbon-oxygen bond becomes stronger. Specifically, that bond becomes stronger than the oxygen-metal bond. So that means above that carbon-oxygen line, metals can be reduced by carbon. If you look at the top, you'll see metals like silver, Ag, which is quite stable. Then we see copper. We see tin, which is used in bronze. And then further down, we see iron. They're more tightly bonded to the oxygen, so it takes more temperature. It takes more energy to do it, which is why the early ages started with copper and then went to bronze and then iron as we developed the technology to use it better. The very most stable oxides that are not reduced, so as again oxides or ore, are at the bottom. As you move to the right on the diagram, the temperature increases and oxides become less stable and can be more easily separated from oxygen or reduced. Let's summarize that as the implications of that. The early charcoal fires were hot enough to reduce silver, copper, and tin from the ores. This allowed the Copper Age and the Bronze Age. Again, bronze is a mixture of copper and tin together, and the advantage of that over copper is it's stronger. So if you have a knife blade, if you have a hoe, if you have a sword, it'll last a lot longer. The edge stays sharp if you have bronze instead of copper. But as we learned, as we went to higher temperature furnaces, they were able to separate iron. But that required forced air and really coal to make that work. That technology showed up in Israel about 1000 BC, and that likely led to King David's success as a leader. That once they were able to replace their bronze implements and swords with iron swords, they were much more successful in fighting the countries around them. Let's summarize all the instances of intelligent design we have seen in this presentation. First one, life could not exist without the process of photosynthesis to harvest and store energy. It takes CO2 and is putting it in the form of sugars that can be used by animals. Also, the unusual gaseous nature of carbon dioxide, one of the few oxides that's gaseous, makes it reach leaves, and being soluble in water means it can exit cells effectively. If it was a solid material, it would be very difficult to imagine how this could work. Also, tying back to photosynthesis, the bond strength of carbon is critical in allowing oxidation and reduction reactions in cells. Next point, we could have never powered the Industrial Revolution and built our modern world without large reserves of reduced carbon fuels. Try and go back several thousand years, and living in that case, we would have wood fires, we'd have a few simple tools, but we would not have furnaces, we would not have air conditioners, we would not have running water in our house. So many things that we are used to would just not be available. And finally, getting back to that Ellingham diagram, the metal oxide reduced carbon reaction is a significant outlier from all the other oxide reactions, and that allowed the age of metals, which allowed us to use these things and build our present world.